So problem 3 has to do with the de Broglie wavelength, and de Broglie wavelength is the wavelength of a particle acting like a wave. And so the wavelength is given by Planck's constant divided by the momentum, where momentum is m over v. So here we're told we have a proton. We know the mass of the proton, and we have an electron. We know the mass of an electron, and they're moving at a speed of 4.7 times 10 to the 6 meters per second. Right, so we know the mass of an electron is 9.11 times 10 to the minus 31 kilograms. Mass of a proton is 1.67 times 10 to the minus 27 kilograms. And the speed of both of them is 4.7 times 10 to the 6 meters per second. So basically we want to compare the two wavelengths. Which one has a longer wavelength? All right, so lambda for the electron is going to be h, Planck's constant, 6.626 times 10 to the minus 34 joule seconds. And here we have to use the one that's in units of joules, over the mass, 9.11 times 10 to the minus 31 times the speed, 4.7 times 10 to the 6. And I get 1.55 times 10 to the minus 10 meters. How big is that? That's about 0.155 nanometers. So that's about the size of an atom. Okay, how about the wavelength for the proton? Wavelength for the proton now, I'm going to do the same thing, Planck's constant in units of joules on top. On the bottom, I'm going to put the mass of the proton, 1.67 times 10 to the minus 27 kilograms. Same speed as the electron, 4.7 times 10 to the 6. And now I get a much smaller wavelength. Why? Because I'm dividing by a much bigger mass. I get 8.44 times 10 to the minus 14 meters, and that's a bit bigger than the nucleus of an atom. Okay, so it's much smaller wavelength for the proton than for an electron. All right, now let's do a couple of problems to do with the Bohr atom. So in the Bohr atom, what we have is a hydrogen atom. The electrons orbit around it in fixed orbits, and when a photon of light comes in, it can take an electron and excite it up to a higher energy level, and we want to know what's the wavelength and the frequency that excites an atom from the ground state to the n equals 4 state. So we start off with n equals 1, and then it absorbs some light with the energy of HF, and it goes up to n equals 4. Okay, so how are we going to do this? Well, we know that the energy of the light that excites it must be equal to the difference in energies between n equals 1 and n equals 4. So what are the two energies? Well, remember our equation for the energy in the hydrogen atom is minus 13.6 eV over n squared. So the energy of the light, HF, must be equal to the difference between the energy in the fourth state and the energy in the first state. So it's minus 13.6 over 4 squared minus negative 13.6 over 1 squared. You got to be a little bit careful with doing your negative signs here. If you want to, you could first calculate what's the energy in 1 and what's the energy in 4, and then subtract them. And so I get plus 12.75 electron volts, and I can convert that into joules. Okay, so just the same way I was doing for previous problems. So I want to go to joules, get rid of EV. 1 EV is 1.6 times 10 to the minus 19 joules. So that's just over 2 times 10 to the minus 18 joules. Okay, so now I've got that, I can find the frequency. So I've got the energy, I want to find the frequency. So I know E equals HF. So the frequency is equal to the energy over Planck's constant. So I can do 2.04 times 10 to the minus 18 joules over Planck's constant, 6.626 times 10 to the minus 34 joule seconds. I get a frequency of 3.08 times 10 to the 15 hertz. And the wavelength, remember c equals lambda f, so wavelength is c over f. And again, when you do these, calculating with this equation, c is always on top. It's never in the bottom. So 3 times 10 to the 8 over 3.08 times 10 to the 15 hertz. And I get 9.7 times 10 to the minus 8 meters. Okay, the last question has to do with the hydrogen spectrum. We want to know about the Lyman and the Paschen series. So for the hydrogen spectrum, it was found experimentally that there was a relationship between the wavelengths that were emitted that was some constant, the Rydberg constant, times 1 over n prime squared minus 1 over n squared. And the value of the first n prime determined what series it was. So we have the Lyman series where n prime is 1. The Paschen series, n prime is 3. And of course the Balmer series, which we're not asked about here, where n prime is 2. Okay, so we want to know what's the longest and the shortest wavelength in each of those series and which part of the spectrum do they lie in. So are they ultraviolet, are they visible, etc. Okay, so let's look at the Lyman series first. Okay, so n equals 2, so my equation is 1 over lambda, so n prime equals 2. 1 over lambda times 1 over one over 1 squared minus 1 over n squared. All right, so I want to know what's the longest lambda and what's the shortest lambda. So if I look at this equation here, I want to figure out what value of n will give me the biggest number and what value of n will give me the smallest number. Okay, well, n has to be equal to, it can't be smaller than 1, so n has to be bigger than 1, and an integer, so the smallest value of n I could put in is n equals 2. What's the biggest value of n I can put in? I could put in n equals infinity. And let's not even just try to do logic, let's just put these numbers in and see what we get. So I got 1 over lambda is equal to the Rydberg constant times 1 over 1 squared, which is just 1, minus 1 over 2 squared. Okay, so that's the Rydberg constant times 1 minus 1/4. So it's 3/4 of the Rydberg constant. What's the Rydberg constant? Let me write it up here. I'll put it in red. R is equal to 1.097 times 10 to the 7. And the units are per meter. Okay, so if I put that in, get 3/4 of 1.097 times 10 to the 7 per meter, which is 8.22 times 10 to the 6 per meter. So lambda is equal to 1 over that. And I get 1.22 times 10 to the minus 7 meters. Okay, how about if n equals infinity? So that's my opposite range. So 1 over lambda equals r times 1 over 1 squared minus 1 over infinity squared. So if I divide anything by infinity, it's going to go to 0. So this is just equal to r times 1. So it's just going to be 1.097 times 10 to the 7. So here my lambda is going to be just 1 over 1.097 times 10 to the 7. So my wavelength is going to be 9.12 times 10 to the minus 8 meters. Okay, so I can look at this now and say which one is bigger and which is smaller. Okay, so this is the smallest wavelength, and this one is the biggest wavelength, because they're determined by which values of integers, the smallest integer and the biggest integer I can put in. So when I put in the biggest integer, I get the smallest wavelength. When I put in the smallest integer, I get the biggest wavelength. All right, let's do the same thing for the Paschen series. So Paschen series, now I've got 1 over lambda is equal to r times 1 over 3 squared minus 1 over n squared. I'm going to do the same thing. So I'm going to choose which is my biggest value and which is my smallest value of n. So the smallest value of n I can have, it has to be bigger than this number, otherwise I'll get a negative wavelength. We can't get a negative wavelength. So I got to get an n of 4 is my smallest one. So I've got, for n equals 4, 1 over lambda is 1 over 3 squared minus 1 over 4 squared. Okay, which turns out to be, when I plug in all my numbers, 5.33 times 10 to the 5 per meter. So my wavelength is 1.88 times 10 to the minus 6 meters. Right, the other extreme is to put in a wavelength of infinity, and then I'm going to get r times 1 over 3 squared minus 1 over infinity squared. So again, 1 over infinity gives me 0. So when I plug in all those numbers, I get 1.22 times 10 to the 6 per meter. So the wavelength is 1 over that. And I get 8.20 times 10 to the minus 7 meters. So again, this one is the smallest, and this one is the biggest. So again, if you can't remember which gives you the biggest and which gives you the smallest, just do the two calculations and look at them and see which number's bigger, which one's smaller. All right, so the last thing it asked was which part of the spectrum do they lie in? All right, so if I look at, let's look at this one. This one is micrometers, and usually when you look at the spectrum you put it into nanometers. So this one is 1880 nanometers, this one is 820 nanometers. So remember, visible light was something like 350 to 750 is visible. Okay, so these wavelengths are bigger than the visible. Okay, so that puts me in infrared. Okay, if I look at these ones up here, these wavelengths are something like 122 nanometers and 91 nanometers. So this is a very small wavelength. And so these values here are actually below the visible. And so these are ultraviolet. All right, if we'd done the Balmer series with n prime equals 2, we would have got wavelengths that were in the visible range. And so in the visible range, those were the ones that were first seen. And so the Balmer series was the first spectrum of hydrogen that people knew about.